Today, I'm lucky to have a great speaker, so I'll be introducing him. Alex Wong is an assistant professor in the Department of Computer Science and the director of the Vision Laboratory at Yale University. He also serves as the director of AI for Horizon Surgical Systems. Prior to joining Yale, he was an adjunct professor at Loyola Marymount University from 2018 to 2020. He received his PhD in computer science from the University of California, Los Angeles in 2019 and was co-advised by Stefano Soato and Alan Ewell. He was previously a postdoctoral research scholar at UCLA under the guidance of Soato. His research lies in the intersection of machine learning, computer vision, and robotics, and largely focuses on the multimodal 3D reconstruction, robust vision under adverse conditions, and unsupervised learning. His work has received the Outstanding Student Paper Award at the Conference on Neural Information Processing Systems 2011 and the Best Paper Award in Robot Vision at the International Conference on Robotics and Automation 2019. So let's welcome our speaker for today.
Thank you for the great introduction. I don't know if I'm a great speaker and stuff, but I'll try to live up to the hype. And from the introduction, you know that I've served as an adjunct professor and during my PhD and during postdoc and stuff. So I do like to teach, and so today, the talk is not so much as to just show you fancy things. Hopefully, we can have some takeaway from this and stuff. So that's why it's called a know-how. We're going to dig a little bit deeper into the little bit of technical things here and there, and it's about depth estimation from multi-sensor perspective and such. And so hope you guys enjoy it. All right, so just to start off, deep neural networks are these highly parameterized functions that have seen a lot of empirical successes across a number of computer vision tasks and other disciplines as well. And because of their sizes and such, they require tens of thousands to millions of training examples, which really amounts to thousands of hours of manual labor and curing just a data set. For those who have labeled data sets before, this is extremely painful. And so, for example, right here, what we have is a data set designed for image classification, where each training example is comprised of an image and its associated class, like dogs, cats, boats, sailboats. But let's consider a different task, for instance, depth estimation. This problem is where we want to estimate the distance of world surfaces from the camera as a point cloud, as a 2.5D range, or a depth map, depends on what representation you want of it from an egocentric point of view. Now, here are just some examples of three-dimensional coordinates estimated through triangulation or returned by some range sensors. And these sparse points tend to be noisy, but they're sufficient for what we call localization, or to estimate the motion of the sensor. But they tend to be a poor representation of the shape of a 3D scene. And so the empty regions here could be points, they could be empty, or they could occupy a surface. We don't know. In order to support some spatial tasks, such as autonomous navigation, manipulation, one would hope for higher fidelity reconstructions. And of course, this also can be done through a deep neural network. But unlike ground truth for classification, which is just a label, ground truth for depth estimation requires a massive effort. For example, one image label for a data set like ImageNet requires a few bits of annotations, and this is in the form of a class label. But for depth estimation, it is on the orders of megabytes in the form of point clouds or depth maps, like those colored range maps you see on the right. Especially in this case, it involves manually selecting correspondence between laser and camera images. This is for calibration, after which these measurements are aggregated over a number of time frames, and all the ambiguous regions such as windows, fences, they're manually removed, and then they get cleaned up and such. And then finally, known object models are then inserted to get those ground truth there on the very bottom. And what this amounts to is really this laborious labeling effort that's extremely expensive and not scalable. And to move ourselves towards a more scalable learning paradigm and such, we'll assume that we're equipped with a typical sensor platform that includes optical, for instance, a camera, inertial, accelerometer, gyroscopes, nowadays range sensors, sparse time of flight, LiDAR, radar. And for most of you in the audience, you might already own one of these devices and interacted with it on a daily basis. Any guesses?
In car?
Yeah, very good. 5 points for UMass. You'd be surprised at how silent it gets when I ask that and such. But yes, it's your phone. And the question is, how do we leverage these rich sensor suites to move away from the supervision in the form of manually labeled ground truth and learn how to estimate three-dimensional structures of the environment from the 3D scene without any human intervention? And so being able to do so would allow us to save on the massive amounts of manual labor, but more importantly, learn online, adapt our inference on the fly to novel data, And to me, this is the first step to understanding the physical world. Vision, I feel like is to actually go back into 3D and stuff to establish separate entities within it and really to enable spatial tasks such as autonomous navigation and manipulation. And to take a step towards this direction, we've designed approaches to train deep networks to infer the dense depth of a 3D scene from images, sparse range, and inertial data. The fundamental idea behind our approaches really is to validate the compatibility between the estimated scene and multisensory observations as a general learning principle. And what I mean by this is that we want to check whether or not the estimated scene can generate the observed images and in sparse point cloud. Nowadays, this approach is very common and such, but back in 2019, 2020, and so this is just when this was budding out and such. And this is done by recreating or reconstructing the observed sparse point clouds and images based on our estimates and other views of the same scene, and then measuring their error. Now, measuring error in the case of point cloud reconstruction entails sampling points from the estimates and measuring deviations between the observed sparse point clouds, such as those color points on the cube on the right. And in practice, the points are first projected onto the image plane as depth maps, and then we measure. This is much cheaper. For image reconstruction, though, we have to do a couple more steps. The first thing we have to do is to reproject the pixels from one image to another based on the estimated depth, the camera motion, or the transformation between these two views we're talking about here, and the intrinsic parameters of the camera. And the training signal, of course, comes from minimizing this reconstruction loss or reconstruction error. And the better we can reconstruct images or point clouds of our estimates, the more accurate the estimates tend to be. In practice, camera motion can be obtained directly from a visual inertial odometry, or a VIO system. In the case of something like frontal parallel binocular stereo, it's actually directly known as the baseline. So training methodology here that I'm describing can really be integrated seamlessly into this online learning paradigm. And what I described here manifests as a training objective or a loss function in the following form. Assuming that we're processing data at each time instant t and such, the first equation up there is the photometric reconstruction term, where we assume, or where we measure the color intensities differences between an image reconstructed from some other time tau and the actual observed image at time t, where I have from tau to t is the reconstructed image. G there is the relative camera motion from time t to tau, and K is the camera calibration matrix or intrinsic camera calibration matrix. The second term there is the sparse depth reconstruction term and such. This measures the deviation of the estimated depth from those measured by some other sensors, such as a LiDAR or radar, or those tracked by a SLAM, simultaneous localization and mappings, or VIO system. And by minimizing some form of this objective, we have shown that a model can continuously learn without any human intervention and adapt to novel environments for both indoor and outdoor, essentially exploit the virtually infinite amount of training data that is observed simply by moving around. And here's a demo where we deploy one of our models to a novel household room. On the left there is the observed image and the depth map as measured by a depth sensor and such, and it's shown there just for reference. And on the right is the plots of the average error over time and the output of the model. Now, right there you see in the first 20 initial frames or so, the error is actually really high, sits around 180 millimeters because the model has never seen leather couches or mahogany cabinets. But soon after, we see a nice little drop and dip, and it continues to decrease to around 30 millimeters as it adapts to this online environment. There are other things as we dig into this later on in a separate topic that we've been exploring in terms of continual learning. But there's a thing called catastrophic forgetting and stuff that I prepare for other talks and such. But we can get to those, maybe another time. But for now, yes, we can adapt online and learn from essentially all of these infinite amount of data. But what I've left out in all of those is actually the essential ingredients is in that reconstructing 3D scenes from visual data is what we call an ill-posed problem. So the solution hinges on the choice of regularization or prior assumptions about the structure of the scene. And these priors or regularizers can encode knowledge about the physical environment, such as the typical orientations of objects as induced by gravity, or generic properties of their shapes like local conductivity, piecewise smoothness, the correspondence of flat surfaces all around us. And they can be learned, of course, from synthetic data, such as that certain local groups or configurations of point tend to correspond to certain object shapes, or even distilled from pre-trained machine learning models. Now, treating these unsupervised learning principles that we have developed as a validation criterion, these regularizers can actually be adaptively applied based on how compatible they are with the observed data. And again, the better these priors can help us model the observations, the more we can trust them, which not only allows us to avoid over-biasing the model, but also to select between different regularizers during this adaptation or training time, or even combine multiple of these things together and such. And just as an example, we can learn one of these regularizers from leveraging synthetic data, where we can basically get virtually unlimited amount of high quality ground truth for free. And these ground truth here, you'll never get in an actual scene and such. And of course, making use of this is not as simple as it sounds, because there exists what we call a covariance shift, mostly photometric, which affects the generalization when transferring models that are trained on synthetic data to real world data. Now, instead, one might observe that unlike photometry, which the covariance shift, unlike photometry, the covariance shift in the shape of objects or the geometry is much smaller between synthetic and real domains, as shown on the top there and such. So those are two range maps from the same exact example that we saw, but you can see that they're quite similar, unlike the images. And for example is that a car, whether synthetic or real, tends to exhibit the same shape, but appearance may vary quite a bit. So using this observation here and such, we can bypass the photometric domain gap altogether by learning the association not from photometry or images to shapes, but that requires a high level understanding of semantics of objects, but from sparse to dense point clouds by using the abundance of synthetic data without having to face concerns about this photometric domain gap. And while the evidence here is only sparse, we have strong priors from the statistics of natural shapes of objects being captured by those synthetic data and such. And this allows us to learn this mapping from sparse point cloud to dense one just by leveraging the synthetic ground truth as supervision. And the output of a network here can serve as initialization, as an input to alleviate any downstream models from having to rediscover what we already know. Not only that, we can use these things to serve as a bias during the course of training as a part of a learning objective or loss function. But because the output dense point cloud there that's being estimated only from sparse points is very prone to error, especially in regions where there are very few or no points at all and such. So instead, we need a way to identify which regions we can trust and which ones we have to fix. And so this is where things become a little bit interesting. Highlighted in red is an example of regions where the regularizers introduces an incorrect bias. So clearly, this is the case where we want to amend it by using the image as in the loss, or maybe use something else in the loss function to reduce its influence. And by using this validation criterion that we just discussed, we can actually measure the correctness of all of these priors and stuff simply by checking if they can generate the observations themselves. And the regions marked in red will yield very high reconstruction error. And this mechanism allows us to determine which area has low fidelity, and in turn, we can amend it or to reduce its influence as part of the loss function. And this is called adaptive regularization. On the right is basically the resulting point cloud where erroneous cabinet regions, which have been fixed fixed from the previous point cloud by validating against the observations. But aside from synthetic data, there exists, another really rich source of this sort of knowledge that we can exploit. And thanks to the rapid growth of deep learning in the recent years and such, if you simply Google awesome, followed by any sort of task names and such, what you'll find is that you'll have a bunch of GitHub repositories, and they are typically, they also release these pre-trained machine learning models and such. Most of the time they work. Sometimes you got to do a little bit of work on your end to get them to work, but let's assume that everything here works, as expected and such, and you can grab all of these pre-trained models to learn this so-called regularizers with. And of course, exploiting these guys as regularizers naturally tend to lend to basically this ensemble knowledge distillation paradigm, which is a way to learn from a bunch of pre-trained models, which we will now call teachers, with the goal of distilling information down to a smaller target model, which we now call the students. But as Mr. Miyagi once said, there's no such thing as a bad student, only bad teachers. So the performance of these students here hinges on the fact that you can choose good teachers to begin with. Now that's easy if ground truth is available, but we said, we don't have ground truth and such. So what we can do instead is to figure out some way of actually distilling these things by making sure that the teacher is actually good at what it's teaching us before we learn from them. And of course, this begs the question of then, how can we learn from this large ensemble of available pre-trained machine learning models without ground truth to basically perform what we call model selection? Now, naively distilling from this ensemble of teachers actually yields a union of their errors and such, because we're no longer looking at tens and thousands of them. We're looking at, which is the case in the classical vision cases. But in this case, we're looking at maybe like 3, 4, 5, because we don't have that much compute. And the only thing that's really helping us here is that they're only being partially mitigated by averaging over these couple of teachers and such here. So for instance, in the middle there, what we see is a model called eNet. It produces errors in the paper cutters, cabinet regions and such. If you distill from this eNet model here, it would introduce these things to the downstream student model. So then the goal is to selectively combine heterogeneous ensembles of teachers in a way that we can leverage their strengths, but avoid error modes like that. And it turns out that our validation criterion does exactly that right there. By validating the predictions of each of these teacher models against the observations, we can select specific teachers to bias specific regions of the estimate during the course of training without the need for ground truth. And you might ask, well, what happens if none of our teachers are great? And so to avoid sort of distilling the error modes that's common to all teachers there and such, we'll propose a function that monitors their performance. This monitor is manifested as this adaptive weighting scheme. In some sense, this monitor is analogous to sort of a superintendent in the school. And here, places with higher errors will yield lower weights to limit the influence of the mistakes made by the teachers. And instead, whenever everything is common across, or whenever errors are common across all teachers and stuff, we'll fall back onto basically this image and sparse point cloud reconstruction loss that we've described earlier. And we call this process monitored distillation, or MONDI for short. Here, what you can see is that the predictions that the downstream student model takes on, some of the characteristics of eNet and this KBNet, such as those sharper boundaries you see on the edges of eNet, but the correct predictions are file cabinets and the paper cutter for KBNet. And the more comprehensive figure down below, we compare across some of the output of each teacher and their error maps and such. And interesting, what you see is that every single one of these teachers have different error modes, some on the walls, some on the countertops. And what MONDI helps us to do is to find a way to select these teachers, combine their correct regions together and stuff to yield overall lower errors. And this in turn allows us to learn from a blind ensemble. So we have no knowledge whatsoever of the ensemble of teachers. And this can be a collection of priors from pre-trained models, synthetic data, generic properties, who knows? But MONDI allows us to take all of these predictions and check against the reconstruction errors and stuff, which in turn gives us something called positive congruent estimates. And through this monitor distillation process and such, we can actually squeeze down models so that they're much smaller and actually get comparable performance as those that were trained on ground truth. And just as a demo here, just by incorporating this bias in the learning process, we've been able to realize models that are about 79% smaller in size and 89% faster than the best supervised models while being comparable in accuracy. And amongst the unsupervised distillation methods and stuff that we saw at the time of publication, we ranked first on Kitty for outdoor driving and on Void as well for indoor VIO datasets. And amongst all methods, including those trained on ground truth, I believe we placed 5th on Kitty and 2nd on Void. And for those who are unfamiliar with these two data sets, they're basically standard benchmarks that everybody are comparing on and such. And so the demo on the right is our model deployed on a commercial laptop, and we ran it in real time to infer the scene structure from a common study room area and such. In the bottom panel, what you see is the output of the depth sensor, again, just for reference. And on the right is the output of our model, both visualized as a 2.5D range or depth map. But now that I've described how you can get these things to work fast and accurate so you can put them on your laptops or even hopefully on robots and stuff, admittedly, they're quite fragile in the sense that small imperceptible perturbations of the input tends to cause gross large errors in their outputs. For example, the simplest case is if you were just to switch the sensor. So embarrassingly, this is the reality and stuff sometimes that we're dealing with. You swap the sensors, all of a sudden you get strange predictions and such. And so here's an example of a point cloud outputted by an existing method. This model was trained on Void, a dataset collected by Intel RealSense, and is tested on the outdoor bench also collected by the same sensor. But when you take this thing and move it to a different sensor platform, which is usually the case when you deploy something in the wild and such, the performance degrades significantly. Here we have the same exact model trained on Void, but test on images and sparse point cloud from NYUV2, which is another benchmark that's collected by Microsoft Kinect. On the right is not so successful reconstruction from this bedroom scene, and surface sort of bowed and distorted a little bit. And for those who have done stuff in 3D vision and stuff, you probably know where these things usually come from and such. And so we're going to dig into that in a second. And what one might hope for is something like these figures in the bottom, where a model trained on one data set collected by one sensor, such as the Intel RealSense, can generalize to novel scenes collected by a different sensor, like the Microsoft Kinect. And to understand how we go about doing this, we're just going to dive a little bit deeper into the details. And as a motivating example, we're going to look at this image on the right here. The generalization problem that we're looking at really is rooted in both the training data collected by some sensors, as well as the training objectives, so what we've proposed earlier. And if we take a look at this figure, these are images taken of the same scene by two different cameras from approximately the same location. For visualization purposes, we just crop them to the same field of view just for comparison. And already you can see objects project very differently onto the image plane depending on the intrinsic calibration parameters of the camera. For instance, the focal length. And so now you imagine if the camera used to capture your data on the left is used to collect your training sets, the one on the right is now equipped onto your test time agents and stuff, robot, for instance. It's not going to transfer very well. And so this generalization problem is further than exacerbated by the unsupervised learning paradigm that we discussed earlier, because the objective that we have designed actually bakes in some of these biases about the camera calibrations. And so specifically, here's again the photometric reconstruction term we talked about before. To compute it, we need a couple of things. First is the intrinsic camera calibration matrix K that takes us between camera and image space. The second is the relative post G here that tells us the transformation between the two frames that we want to reconstruct from. The third is the estimated depth D hat. And so in this case, pose and depth highlighted in blue are jointly optimized, and calibration circled in big red there is assumed to be known and typically only utilized in the loss. And it can be seen that if you minimize any form of this loss function and such, the network actually gets forced to implicitly learn and bake in the calibration matrix. And so for pre-trained machine learning models that are commonly deployed across different sensor platforms than those used during training, this actually hinders generalization. So how can we deal with this? Well, one way is that we can pre-process all of these images some canonical calibration. Great, but then that's slow and introduces latency, artifacts, and we're going to train on these things and such. So that's going to mess with our reconstruction quality, which then affects the training signal and also the accuracy of the model. What we decided to do is, well, if it is different camera models that we're looking at and such, then let's take the image, the projected sparse point cloud, and the calibration matrix as input. And this, first of all, allows us to use different calibrations during training and test time. The figure here illustrates a deep neural network architecture called KBNet, or Calibrated Back Projection Network, where we explicitly implement the back projection process as an inductive bias within the network architecture. And so here's how it works. First, we'll lift the pixel coordinates up to 3 dimensions and then use calibration to transform our points back to the camera, which are then back projected using the imputed depth D. And this results in what we call three-dimensional or 3D positional encoding in the canonical camera space, where the calibration is no longer a factor. It's concatenated with the image encoding and the output of previous layers and such, and then fused together using a one-by-one convolution. So it's quite cheap. And of course, this gives us what we call an RGB 3D representation, which can be used as a skip connection or as input to subsequent layers and such. But this architectural inductive bias here doesn't just improve generalization, actually. It enables us to use some different calibrations at test time. That's one thing. But it also improves performance by delineating between points that are close in the 2D image, but far in the 3D scene. So if you just take a picture of me right here and such, my face is very close to the wall in this 2D image, but very far in 3D and such, right? So in reconstructions, what you tend to see is these bleeding effects where the points will sort of get smoothed out into this wave-looking thing and such. And so this particular design here helps us mitigate some of those, and we get a lot sharper boundaries. Now, training KBNet is pretty straightforward. We just have to minimize the same predictive cross-modal validation criterion that we discussed earlier to measure how well the estimates can, again, reconstruct the multi-sensor observations. But even though we're training with the exact same loss that we mentioned was problematic, we show that this network design, based on our understanding of how the image formation process works, actually significantly improves generalization across different data sets and such, and yields a much smaller model that is faster and more performant than computer methods at the time. And shown here is a figure where we now are able to correctly reconstruct the scenes that existing works failed on earlier. But while we can talk about this architectural inductive bias about different intrinsic parameters and such, the most common source of covariance shifts actually stems from external factors, such as novel, possibly adverse test time conditions. And so here we show some of the state-of-the-art models on Kitty, and if you transfer them to other data sets that actually include some of these adverse conditions and such, maybe changes in illumination, weather conditions, rain, snow, they actually predict very terrible depth maps over there in blue. But if someone were to give you the testing data, right, can we make use of it? We don't want to just waste it and such. Can we make use of the testing data and perhaps update the model online in some unsupervised manner in real time so that we can adapt to these adverse conditions? And to answer this question, we have to look at how these models are affected by each modality in the source training and target testing domains. And while operating in the source domain and such, the first observation that we make is that if you use everything, all the modalities that you have, this gives you the best results. In fact, taking any of those things out, replacing them with something else and stuff, is going to introduce catastrophic errors. But in the target testing domain, what we observed is that the opposite happens, where if you use all the modalities together, the error drastically increases. And it turns out that the image modality is so sensitive to this domain gap that if you forego it altogether, as in take away the image, toss it away, you actually end up with better results in the test time domain. Interesting. And so taking this intuition, we are going to try to close this domain gap and such. And we want something that's fast, that we can do with a single step of update and mitigate this covariance shift. So what we're going to do is to deploy a single layer to adapt the model for the modality that's sensitive to this covariance shift. We know that is the image in this case. And this is done at test time by using other modalities to predict what would have been the embeddings in the source domain for both. And to do this, what we're going to start with is actually this preparation stage in the source training domain that is visualized in the yellow diagram at the top. And what this entails is really just learning a set of multi-layer perceptrons or MLPs that take in just one of the two modalities and predict the embeddings for both. Now, we're going to call these things proxy embeddings because they are the embeddings, but through the proxy of another. And once trained, we're going to freeze these guys and take them to the test time domain with us. And at test time, we're going to make two forward passes. The first one is being shown in the purple diagram there. The first one, we're going to forego the modality that's sensitive altogether and use the other one to predict the late proxy embeddings for both in the source domain. In the second forward pass, we'll feed both of them together in to get the test time embeddings. Now, we're going to use these proxy embeddings to guide the updates of this adaptation layer. And of course, this can be realized as a regularizer that biases your test time embeddings to similar to be those in the source domain. And this can be used the unsupervised losses that we just talked about for making these model updates. And just to show you what I mean by this and the intuition behind that and such, the effects of this regularizer with a proxy embedding really is analogous to translating the embeddings from the target domain back to the source. And on the right, there is a TS and E plots that visualizes the centroids of the source domain embeddings that's given by green and black stars there. I don't know if you can see, which are pretty far from the red one and stuff down below, which are the embeddings from the test time domain. The test time proxy domain actually is visualized in blue, and you can see how close it is to the source domain so that we can use them as a regularizer to close this gap. So what we're doing here is really just to use the complementary properties of different sensor that's invariant to these test time conditions to translate us back over and use these things, of course, knowing which one's the sensitivism is another problem that we have to discuss later on and such. But being able to do this and stuff actually has a lot of implication towards robustness, resiliency for multi-sensor fusion. And adapting a couple of these publicly pre-trained machine learning models of our method can achieve 11.6% improvements over the best existing methods. And here are just some head-to-head comparisons between the outputs of the pre-trained model and that of the adaptive model, where we're able to recover high fidelity depth maps during nighttime and during rainy weather. And these are being tested on Waymo, which is another self-driving data sets for outdoor settings. And these results were just achieved with a single update step. And because we have to update just one layer and such, this makes our method very fast and pretty suitable for deployments. And that's what you see on the bottom, or on the panel on the right side there and such. The pre-trained model adapted in one step towards the test time domain gives you those high fidelity depth maps on the right. And of course, so we've gone through this sort of unsupervised training objective. We've gone through various regularizers that we can exploit. We've gone through how to adapt these things on the fly online. But we never talked about how to actually train one of these depth estimation networks, right? So here's where we kind of dig into a little bit of the actual operations that we have to do to get these things working. Starting with the data, we're given this image sequence of synchronized images and point clouds projected on the image frame as sparse depth maps. And the photometric term that we talked about before only constrains the solution in regions where there are sufficiently exciting textures and co-visible between the two frames, such as those highlighted in blue, green, and orange there. And of course, the sparse depth reconstruction term only constrains solution anywhere there exists a sparse point. Everywhere else, we have to rely on the regularizer, which is why the regularization is such a big part of reconstruction problems. And as in, of course, the typical training pipeline, the first step, of course, to augment your data, right? So we're going to enrich our data set by orders of magnitudes. And of course, the figure here shows the inputs after we applied a bunch of photometric geometric transformations. And there is a problem. The previously exciting textures that served as our supervision are now largely saturated intensities, homogeneous in contrast, and they can no longer be uniquely matched. So the sufficiently exciting texture things are all gone out the window. And we can't apply any intensity transformations to the sparse point cloud because doing that would alter the 3D scene. But simply applying these same geometric transformation, you can see how the points have kind of been decimated and reduced in the depth map below. And just to show you side by side what that looks like and such, here's that figure. In fact, for most vision problems, it's very typical for conventional augmentation schemes to introduce saturation image intensities, block artifacts through interpolation, loss through resampling and such. And this causes a loss of photometric correspondences between the images and a loss of points in the sparse depth map for us. Now, to most other vision problems, these are actually desirable side effects that we want, because for something like object recognition detection, you want to learn representations that are invariant to all of these nuisance variability. This is not the case for unsupervised depth estimation. And this is because the training signal comes directly from reconstructing the inputs, image, and sparse depth map. So the more we augment our data, the more we degrade the training signal. So it's not too surprising that conventional augmentation methods for all of these molecular depth estimation completion tasks and such have seen very little use beyond, say, small intensity changes and flipping. But of course, photometric augmentations are important. They help us model diverse range illumination conditions, object colors that may populate the scene. Geometric augmentations can simulate various camera orientations and stuff, motion, and as well as their intrinsic parameters, for instance. In-plane rotations can model your camera orientation. Resizing operations, of course, can simulate different intrinsic parameters, largely in the focal length. And of course, you can translate and such, and these are the principal points and such that are being modified. These augmentations are often viewed as essential for all other vision tasks, but it's detrimental for us. But now without them, we're going to run into issues of robustness and generalizability. So at this point, we're at an impasse. This was a very frustrating point about a year and a half ago and such. And so the question that we asked is, how can one apply a wide range of augmentations without compromising the supervision signal? Well, if it's a supervision that we're concerned about, well, let's start by reconsidering one of the loss computation steps and such. And the inspiration of this actually came when I was teaching Intro to Computer Vision. I think it was lecture 2 when we talked about transformations. And our idea is very straightforward. If computing the loss on the augmented images is detrimental towards our supervision signal, then just compute the loss on the original images without any augmentations. Well, what if we were just to feed forward all of these images and such and see what happens? Turns out that we're going to have a problem, as illustrated there and such. If we were to first perform your photometric augmentation of the image and then the same set of geometric augmentation of both the image and sparse depth maps, afterwards, what you get is going to be a dense depth map that is no longer in the same reference frame as the original inputs. So we can't compute a meaningful loss from this procedure. Well, what does lesson 2 from Intro to Computer Vision tells you? Well, we work with something called group transformations. And those guys are really fun. If there was a way to just warp these things back to the original frame of reference by applying the inverse geometric transformations onto the coordinates and such, then we're in business. And we call this process aug-undo, where we literally undo those augmentations performed on the inputs, but for the outputs. Now, for photometric transformations and such, this is simply by choosing the original intensities to compute the loss on. For geometric transformation, this is done through a series of inverse warping steps where we can now take advantage of these group transformations that are often used in typical augmentation procedures, where we can easily obtain their inverse transformations. And of course, the inverse warping step therefore involves composing all of these inverse transformations together first, then performing a resampling with the output depth using bilinear interpolation, and just so that this entire process is fully differentiable. And once transformed back to the original frame of reference, we can now compute the loss on the original inputs, so these ones right here, without compromising the supervision signal, but still reap the benefits of augmentations. And so aug-undo enables this wide range of previously infeasible photometric and geometric augmentations for learning unsupervised depth. It can be applied in a plug-and-play manner to scale up augmentations of existing methods in both monocular depth completion estimation. The difference between the two tasks really is just whether one has access to sparse point clouds. And of course, this method is only needed during training and incurs negligible costs. So any performance boost you get there is essentially free. And to test out our approach and such, we evaluate ourselves on, again, Void for indoor and Kitty for outdoor, and found they gave the consistent improvement of 11.7% across 4 different methods over the 2 data sets. But the improvements are not just limited to the data sets that we train on and such. Aug-undo also improves zero-shot generalization to 3 other data sets by an average of 21.3%. And so visualized here are some head-to-head comparisons trained using the traditional augmentation schemes that everyone has been using before, and those trained with aug-undo. And we found that methods trained with aug-undo consistently yields less border boundaries for sure. And this is because we can translate the image out. So this simulates occlusion by motion. But when you compute the loss, you have all the correspondences back. So this allows you to get rid of those guys and such. It also plays a big role in giving us predictions that are consistent, or having some level of consistency when you have objects in different orientations, because we can now rotate, resize, we can do all of these different things, especially when we switch again to different cameras. And now we're going to try to wrap up a little bit and just give some bigger picture detail. Since we talked about how to train, we've talked about how to adapt, we've talked about how to use different regularizers and such, some of the pitfalls that we have introduced when we first came up with these objectives back in 2018, 2019. But in the age where deep networks are more data hungry than ever, now we're looking at millions, tens of millions of training examples and such. You guys may have heard something called depth anything, 63 million plus training examples, all through the pseudo-labeling process. These pre-trained weights are becoming the de facto way of initializing models, such as Dino, ImageNet. One might wonder, is it possible for us to leverage this unsupervised learning for depth as a scalable form of pre-training? Because all we need are just videos, run a VIO through them, and it seems like you're pretty much set. So specifically, we're looking to take these pre-trained weights from depth training and checking if there's viable options for us to fine-tune for downstream semantic task. And I'm so happy the answer is yes. Because I was a little bit skeptical and such, because there was papers from Berkeley saying, it's called taskonomy, that says geometric tasks, they're no good for semantic tasks. So Alex, you're screwed. But gladly, we tested these things out on a bunch of different depth prediction models and stuff, and also different data sets to find that indeed that we can transfer these depth prediction models down to semantic segmentation and detection. And what we observed is that if you initialize these models and such with pre-trained weights from depth estimation, it generally improves over, say, ImageNet, which was our bar for whether or not this is viable and such, because everybody uses ImageNet. Some people use Dino. And we show our results on Kitty and NYU V2 data sets here. Despite one being an indoor data set and the other one being outdoor and such, we actually see very similar trends in their mean intersection over union MIOU. Not only do we get a boost in performance, first of all, but we see the loss is consistently lower with a faster convergence rate during training. This is a good sign for us. And our conclusions hold for both convolution-based and transformer-based architectures as well. Now, when compared to all of the common pre-training paradigms on the right over there, depth is actually comparable to supervised pre-training on COCO, surprisingly. And this came, quite surprising to me in first and such, but because something like classification or contrastive-based learning and such, these are more semantically related tasks because you're trying to basically map things to equivalent classes. Depth estimation here is not. It is actually a geometric task, so it seems sort of far. But after we thought about it and such, the transition seems natural, in fact, because what is a range map? Well, a range map is a piecewise smooth function defined on the image domain, whereas a segmentation map is a piecewise constant function where the levels of the labels and stuff, or the levels of these things are mapped to arbitrary labels or classes. And as a result, representation supporting depth estimation seems to be easily modifiable towards some semantic segmentation. And aside from this, we dug a little bit deeper and tried to push the limits in terms of training set sizes, and found that pre-training on depth also plays a role in sample complexity, as it at least consistently improves over ImageNet pre-training when given fewer samples for a downstream task. So we tried to increase number of examples and stuff, and you can see how the trends start to converge. But in general, depth does better. And the visualizations that we saw in terms of the outputs and stuff also gives better segmentation boundaries and fewer spurious predictions and stuff. And this is expected because these are dense prediction tasks. But aside from segmentation, we also found that depth pre-training is actually improving object detection as well. And so indeed, learning from depth is actually a very scalable way and viable way to as an option for pre-training on semantic tasks. And of course, with the potential of transfer then, one would wonder if, well, can we add more modalities to this? Maybe including tactile, audio, many more and such to serve as a generic representation. But expanding number of supported modalities actually is prohibitively expensive because it requires synchronized data collection across all modalities. Then you got to train all of them together. So nobody has that kind of compute, at least not us at Yale and such. And to further complicate matters, turns out that even within the same modality, you have returns from sensor that has different specification, and those have really big variations. So think fisheye, panel, or different types of tactile sensors. And turns out training on this heterogeneous collection of images ends up giving you something that performs worse than training on something of the same exact intrinsic parameters and such. And we saw some of these things in the earlier slides, and they sort of hinted at this phenomenon as well. And so one question that came to us was, well, does this mean that we have to train a different encoder for every single one of these different sensors? Because that's just terrible. So then we wondered, well, how can we build, say, foundational multimodal models in a scalable way? Is there a way that we can kind of scale up all these modalities without having to give everybody their own encoders and such? And given that conventional multimodal training aims to really align features extracted from each modality to a common latent space, for example, contrastive learning, we're going to leverage this property from these pre-trained machine learning models. And knowing that this gives us already a space that is semantically meaningful because we're attributing text or labels or words to images rather than collecting a synchronized data set and train them all together, we'll just exploit the latent space there and align new modalities to it. And this comes as a form of new encoders if we have a completely new modality, but we have existing ones and such. Then we don't have to deploy a new encoder, but we want to use a few, say, small set of parameters to model the differences between these different sensor specifications. Specifically, what we're going to do is take one of these existing pre-trained multimodal models, freeze it, and rather than collecting synchronized modalities for synchronized data for all the modalities, we're just going to collect it for two, any two that you choose, one existing and the new one. And when given a modality and such, or the new modality, we're going to deploy a new encoder along with a small set of parameters. This comes in the form of a pool of tokens that will be given to the model as inputs along with the data. And these sensor tokens are used to model specific properties from calibration to intensity profiles and such of different sensors, and are used to select, essentially, which specification that we can use to capture the inputs. And we demonstrate this on tactile. For those who have worked in robotics, tactile is the worst thing anyone has ever came up with and stuff because there's no standardization across sensors, so everything comes differently. You take something from a gel cell, you take something from a text, nothing looks the same. So it's incredibly hard. And so our method here really is a way to handle the heterogeneity of different sensors. And because we're only training a few tokens and stuff, it's very inexpensive to acquire a small data set for. And once trained, this model can now support novel modalities for a number of zero-shot tasks, including material classification to touch understanding, where we're able to improve by an average of 9.3% over 6 data sets. And relative to robotics and such, we also improve graspability prediction by 5.6 across 3. And as we have aligned new modalities to the existing ones, we're also backwards compatible with previously demonstrated systems, including stable diffusion, where we can now do image synthesis and restylization. Of course, this wouldn't be 2024 if we don't talk about large language models. So we have also demonstrated that we can connect our representation to LLMs to do some question answering about material properties and make some predictions about robotic tasks. And now just to wrap up and conclude about the know-hows and stuff that we've discussed, we talk about approaches really to learn unsupervised depth estimation without any need for manual labeling. Now this is basically measuring geometric consistency between the estimated point cloud and multi-sensor observations. And we saw that the regularizers, or these prior knowledge assumptions, they play a really big role in this ill-posed problem in terms of speed, complexity, and performance. But as we dug a little bit deeper and such, we found that the limitations really is in their generalizability to new sensors, to new domains. And so we designed some approaches to model their calibration, to adapt them online, and to alter their training procedures to now enable some of these previously infeasible augmentations to improve their generalization. And as we scale up these training procedures and stuff, despite being trained for a geometric task, these representations exhibit pretty good transferability to downstream semantic tasks and such, which gives us now a new way of doing unsupervised representation learning. And motivated by these findings and such, we've expanded the modality supported by our models as a way of building foundational multimodal representations at scale. And of course, we're not the only ones thinking about the alternative sources of supervision as well. There are plenty of people working in this area. It's a very hot area and such right now, developing ways of making these things more scalable, more performance. Others in the community have considered tasks such as contrastive learning, mask autoencoders, and other self-supervision and such techniques. But given what we have seen as these initial steps, and really, I think we've barely scratched the surface and such, our results have been pretty promising, both basically to scale and in terms of performance and such. And so I think what we really want is to spark some conversations and continued investigation into this line of work, made for other geometric tasks, as a new avenue for large-scale representation learning. Thank you very much.
Yeah, okay, thank you. Great talk, really
thank you.
enjoyed it. My question was more on the last part on depth pre-training for segmentation.
Yes.
So one question, does it matter the types of scenes and segmentations tasks you're looking at for this conclusion to be true? So for example, outdoor scenes, there's a strong correlation perhaps with depth maps and objects because things are moving in this scene, but would that also hold for indoor scenes or things in other data sets?
Yes, actually, that was one of the things that we found. So the initial experiments that we had was only on outdoors. And so we trained a bunch of stuff for Kitty and cityscapes, and I think we threw in a couple other ones and stuff that we found online. And it didn't work for indoors at all. Then we said, oh, well, of course, and these things are trained for outdoors and such. Why not throw in some of the mixed up indoor data sets with it? And then that's when things becoming more concrete. And then they can transfer it to indoors and such. So that's why we saw them here. Eventually, we started testing on depth anything. So in the transformer architecture and stuff there, I think that was DPT, which is one of those things trained on, I think, 11 million images indoor and outdoor and such. Eventually, we hit right there, 63.5 million. I think that one is depth anything. So as we expand basically the pre-training data sets, we also see consistent improvements in the performance for downstream tasks as well. But that's a great question. That's something that I omit to tell just for the storytelling part and stuff. But yes, you have to train on everything.
And then does the other direction also hold? Like if you were to improve semantic segmentation, does it help you do depth better? Or?
So this is a great question. We never tried, but what we found was that if you were to initialize something with, say, ImageNet pre-training, right, then depth obviously gets better because it now has filters that's been seen on 1 million images and such. It also, if you now take depth and move it back to semantic segmentation, it then helps the segmentation task. So sort of you see this nice little cycle and stuff to see if we can transfer some of these things back and forth. In the end, even though it's the same data, you get something better out of it. So it's a phenomenon that we're looking to investigate, but we haven't done too much work in yet.
Thank you.
So my question is quite simple. I just want to ask, like when you're using multimodal, like image and the range image to do the test, and you says like sometimes if you just give the model the range image and it has better segmentation performance, do you have any insights on why this might be true? Because from my perspective, you should probably give the model the full information of the actual scene, and then the model then be able to kind of do the inference. But it's kind of like I'm not expecting like if you give a null and a range image, the model can give better performance.
Right. So so that was not for segmentation, but for the same depth estimation task and such. And this really comes from the fact that there is what we call a covariance, as in the changes in the inputs affects the outputs. And for something like images or photometry, essentially, this is measurement of lights. And so you can imagine that me turning off the lights or me changing to a different lighting source, or even me waving my hands and stuff, shadows all over the place. This is going to affect the image a lot. But for something like a point cloud and stuff, regardless, this is a 3D point. That's the coordinates of it in 3D space, right? No matter how I wave my hand, no matter how I change the lights, that stays consistent. So that's why it turns out if you throw away the image, you actually get reasonable results with just the input point cloud. But if you toss away the or if you use them both together and such, then you actually take into account that covariance shift and your predictions go haywire.
Got it. So a follow-up question here is like you just identify like which modality plays a more important role in your empirical way, but there's actually no some way that you can detect those kind of behaviors before you actually run the experiment?
Yes, so this is actually our ongoing work.
Okay.
So this is our next step, and stuff because we said, oh well, of course, not all modalities are equivalent and stuff, and this makes sense because otherwise there will be a universal sensor, right? So each thing has sort of these what I call complementary properties and such that can be used together. They all capture different information. I'll put that in quotes. And so here we're saying that we've done the empirical tests and we've found this one observation, so we're going to leverage it. But of course, we can't identify off the bat which one is most sensitive because that's actually a pretty hard problem. Depends on what you're trained on. Depends on what sort of networks and stuff you're using and stuff as well. So that's actually an ongoing project we're doing right now to investigate this. In fact, I think a few months back and stuff, I wrote a grant just on that part because I was like, oh, this is such a hard problem. But yes, great question.
Thank you.
Maybe one more question.
Really enjoyed the talk.
Thank you.
I had a question. I've been seeing a lot of work sort of they predict like relative depth instead in order to get around this problem where it doesn't generalize across like different cameras or camera parameters. Do you have any opinion on how like predicting relative depth compares to some of this work, maybe in terms of like how it would generalize to other cameras?
Sure. Yeah. So there's actually a couple of things that determine scale. The first thing is if you give me a single image, nothing you can do. You cannot guess scale. So any form of metric depth you get is essentially hallucination, or it is really the bias that you get from the data set. So that's why they don't generalize. Well, if you just turn one of them. Now, how do you generalize? Well, there's a couple of key elements. Calibration plays a huge role because that gives you basically scale of the projection and such. So if you take in 3D vision, then there's a couple of key elements, calibration being one of them, to help you get scale back. Now, so that's why in our investigation here and stuff, we actually use calibration, and that allows you to start generalizing for metric scale. The metric scale here is actually grounded by the sparse points. So before using calibration, actually, we're just stuck on one data set for the most part. But once we plop in calibration, now it starts generalizing. Now, the alternative way is that you go with the inverse depth case and stuff at relative depth. So no calibration needed, no points needed and stuff. Give me an image, I give you how ordinal things are placed in the scene and such. Now, for that to work, what we found was that, or at least we actually tried that in the very beginning as well, because there was a lot of monocular depth estimation things a few years back that was very popular. Turns out it doesn't generalize either. It is actually the data that you train on that helps it generalize to that scale. So that's why the most successful methods in monocular depth estimation, DPT, I think is 11 million. Depth anything, 60 something million. And then I think now there's some unidepth and other things and stuff. And Bladden just had a paper on this thing called Depth Pro. I think that's in the orders of like hundreds of millions now and such. And that one works the best, of course. But I think right now it's turning into a data-driven problem, to be completely honest. And so that's why we're looking at other sources of ways to kind of to determine scale in this case. But tangentially, if you had something else, such as texts or descriptions of object in the scene, this is an old problem called semantic mapping and such. If you know that there are certain tables, chairs, or whatever, and they have certain sizes and such, you can use that to get back your metric scale, supposing, again, you have calibration and such. And so that's actually some other stuff that we've been working on to use language to now provide us with scale while taking advantage of this relative depth predictions that other people have spent some 63 million data points on.
Thank you.
Yeah, I think let's thank our speaker. Thank you so much.
Thank you very much.